In the last episode, Professor V.J. Balasubramanian told us how the universe might be a hologram from information at the edge of the universe. But today, let's look at a more conventional possibility from Claudia Durham, who is a professor of physics at Imperial College London.
It's always really great to be here, so thanks a lot. And so in exploring the mysteries of a universe, gravity is one of the phenomena that plays the most important role. And so we really need to understand gravity at a very fundamental level.
She starts off telling us that gravity is the backbone of cosmology, a much more conventional exposition of the Big Bang universe.
You can think of the fabric of space-time as a patchwork of events in space and time, and gravity is a thread connecting between them. And in fact, when we zoom into the largest possible distance scales, to the cosmological distance scales in our universe, we already have strong indications that our universe is behaving in, let's say, mysterious ways.
She tells us that as we move into cosmological scales, the universe is not behaving as it should. It's behaving very strangely. Let's find out what's wrong.
For those of you who can see the screen, you'll see an animation zooming out of the solar system, zooming out of the galaxy, zooming out of a cluster of galaxies, over distances of billions of kilometers. It would take us just a few millions of years to get there if we were able to travel at the speed of light, which we can't, which we won't. And what we see on those huge distances is that it seems that all of the galaxies are distributed along clusters of galaxies, which looks like a little bit like filaments, embedded in halos of dark matter. And they're represented here in blue. These are just fake color. We don't see dark matter because we don't interact with dark matter. But it looks like most of the energy present in the universe is confined along the structure of masses in the universe.
So the problem has something to do with the dark matter. She tells us that the dark matter shown in blue isn't really blue. It isn't visible. It's not detectable at all. But how do we know it's there? Well, it has to be there, otherwise the theory doesn't work. And that is the ongoing story of the Big Bang. When Penzias and Wilson found microwave radiation coming from every direction all around us, three bright theorists, Robert Dicke, Jim Peebles, and David Wilkinson, were sure they knew why. Radiation coming from the Big Bang. It should have a temperature of 50 degrees Kelvin and a specific kind of spectrum. But the temperature was only about 4 degrees Kelvin and the kind of spectrum was also wrong. Even so, the Big Bang was definitely confirmed. But not only the temperature and the spectrum, but the distribution of the radiation was also wrong. It should have been an uneven pattern of bright and dark patches reflecting the uneven, lumpy pattern of huge clusters of galaxies separated by vast empty spaces. But it wasn't. So at the start of the Big Bang, the universe must have expanded at millions of times faster than the speed of light for just a fraction of a second. It must then have slowed down to less than the speed of light in another tiny fraction of a second. Cosmic inflation had now become part of the Big Bang. It meant fudging a speed to millions of times faster than the fastest speed limit possible. But never mind, we can live with that. After all, the astronomers can. And dark matter came about in the same way. Galaxies appeared to be moving much too quickly to fit in with universes deduced from the Big Bang. To make the theory hang together, there should have been far more mass in those galaxies than they possessed. Since there was no mass visible or detectable in any way, there just had to be invisible dark matter. And as we saw in Claudia de Ram's lecture, it's all as well mapped out as the stars and photoshopped to a very attractive blue. To make the theory hang together, there has to be vastly more dark matter which we can't see than real matter that we can see. And then there's dark energy. The cosmologists found that the fainter a galaxy appears, the more its spectrum is shifted towards the red. They decided that must mean the bigger the redshift, the faster the galaxy is moving away from us. So they devised a means of measuring the universe by the redshifts of galaxies. They assumed that the redshift could be used to measure distance. It was later discovered that those redshifts do not increase gradually with supposed distance. Redshifts go up in jumps. So galaxies travel at one speed for a while, then suddenly jump to a higher speed. How do you explain that? Oh, that's the least of cosmology's problems, so don't worry too much about it. Cosmologists don't. But they devised another way of measuring the universe, using supernova explosions. The two methods of measurement didn't agree. So the theorists solved the problem by inventing a wonderful and mysterious dark energy. This dark energy is even more powerful than the dark matter. It accounts for about 70% of the entire universe, but nobody can detect it or figure out what it might be or where it could have come from. But it definitely must be there, because the astronomers are dead certain about their interpretation of those redshifts, and just as certain about those supernovas. But maybe we should get back to Claudia de Ram's beautiful blue dark matter.
Color. We don't see dark matter because we don't interact with dark matter. But it looks like most of the energy present in the universe is confined along the structure of masses in the universe. And if we look at how objects behave on those distances, what we would see, what cosmologists see, is that the further you look and the further objects seem to be moving away from us. And that happens in all possible directions. And that doesn't mean that there's something specific about us and about where we are and everybody wants to get away from us, which maybe, granted, that's a possibility. It simply means that actually the universe itself is expanding. What is happening is that the very structure of space is being stretched. And so anyone in the universe sees other objects moving away from them, and faster the further away they are.
What can it mean that space itself is expanding? Well, we came across something similar last time with those bendable manifolds. If we take speed as a constant, then either length or time, or both, have to become variables. If we are defining speed in terms of redshift, then length and time depend on redshift. So if you're a cosmologist, you can be in a world which does not behave the way we experience the world to behave. Space itself can expand.
But if there's one thing we know about gravity, is that it is an attractive phenomenon. We are attracted by the Earth, for instance. And so if it were true that most of the energy present in the universe was under the shape, in the form of masses in galaxy clusters and dark matter, we would expect the gravitational pull from those structures to lead to a slowdown of the expansion of the universe. Maybe there could even come a point where the expansion of the universe has slowed down so much that it has come to a halt and the universe will start contracting. At least that's what we would expect if it were true that most of the energy budget in the universe was present in those structures. But over the past 25 years, cosmologists have actually seen exactly the opposite. What has been confirmed over the past 25 years is that the expansion of the universe is not slowing down, it's going faster and faster. The universe is expanding at an accelerated rate. And this is contrary to our expectation if it were true that most of the energy present in the universe was indeed localized in some structure of clusters of galaxies and filaments of dark matter. Anywhere you are, even in the middle of emptiness, you still feel with some energy of what we call the vacuum. This is a quantum energy of the vacuum which fills every pocket of the universe uniformly from here on Earth to the middle of the cosmic voids. And in fact, the discovery of the Higgs boson is the proof that even empty space is filled with some energy, in this case, the energy of the Higgs field. It's a quantum energy of the Higgs field. And that energy has consequences on other particles. And if it has consequences on other particles, thanks to the equivalence principle, we would have expected it to have implications on gravity and therefore implications on the whole of the universe. And this is not per se controversial. It's almost known for about a century that we would have expected emptiness, empty space, to carry energy corresponding to the quantum fluctuations of the vacuum. Now, if we take Einstein's theory of general relativity, and we include this quantum vacuum energy, the good news is that it does lead to an accelerated expansion of the universe. The bad news, because there's always a bad news, is that the expected rate of acceleration of the universe from this quantum vacuum energy is way too fast. And is not just wrong by a factor of 2, a small computational error that you can sweep under the rug. Actually, the expected rate of acceleration of the universe, thanks to the quantum vacuum energy, accounting for particles that we do know exist, for instance, the Higgs boson, is at least 28 orders of magnitude.
That sounds impressive. But there may be those who don't know what 28 orders of magnitude means. It means one with 28 zeros after it. Most Americans would call that 10,000 trillion. The discrepancies seem to be getting bigger. The temperature of the background radiation was only wrong by a factor of 10 times. The speed of inflation was only impossible by a factor of a few million times. Now we're wrong by 10,000 trillion times. And how do we get out of that?
This is the biggest discrepancy in the whole history of physics. This is the biggest discrepancy in the whole history of humanity. This would mean, if it were true, I'm a theorist, so I'm not very good with observations, but I can tell you there's one thing I know is not true. It would mean that the space between you and the person sitting next to you would be stretching so fast that it would go faster than the speed of light and you wouldn't be able to see each other anymore. So, again, I'm a theorist, but I think that's wrong. I don't think that's happening. In phrasing the mysteries of a universe, we often phrase it as surprising that most of the energy budget of the universe is dark, and that components of the universe that we know exist, like you and me, and all of the standard matter, and stars and black holes, etc., only make 5% of the energy budget of the universe. But the real question to my mind, the real puzzle to my mind, is not why is the universe so dark. The real question is why isn't it much darker? Why is vacuum energy not accounting for a much larger proportion of the energy budget of the universe as we would have expected? And faced with the biggest discrepancy in the whole history of humanity, I would say, the standard approach that you may hear of is simply to ignore the elephant in the room. This problem is so big that I'm simply not going to look at it. Maybe it's just going to go away. I'm just going to postulate for a reason or another that this whole hugeness of vacuum energy does not exist. I'm going to set it to 0 for an unknown reason that future generations are going to tell me. And instead, I'm going to postulate the existence of another, new kind of dark energy fluid, which has properties, actually, at the classical level that would have very similar properties to this vacuum energy.
Hey, doesn't this mean that the theory has a 99.999999999% chance of being wrong? Doesn't that utterly unbelievable amount of energy stretching off into the distance, billions of light years in every direction, raise some questions? Well, up to now, whenever the Big Bang had been shown to be untenable, the solution has been to just propose another quick fix with an even smaller probability of being true. Claudia de Rham suggests 2 quick fixes. Just ignore the problem, or introduce a new form of dark energy. She also suggests fiddling with the theory of gravity. But it seems odd to me that when we reach improbabilities of thousands of trillions, none of our brilliant professors of cosmology ask, could it be possible that our theory might be wrong? Or is there an alternative which fits the observations a little bit better? Well, in episodes 47 to 49, and in a couple of subsequent episodes, we met an alternative which fits the observations very well. But that alternative is unmentionable in the establishment's scientific circles. It is utterly banned, and you will be cancelled if you mention it. It's the alternative we find in Genesis chapter 1. The first thing we find there is a mass of water. And darkness was upon the face of the deep, and the Spirit of God moved upon the face of the waters. Then comes a mysterious item called the firmament. And God said, "Let there be a firmament in the midst of the waters, and let it divide the waters from the waters." There are several places where we are told that after creating the firmament of the heavens, God stretched them out. "Thus saith God the Lord, He that created the heavens and stretched them out." Any stretching out process needs work, the input of energy. The waters below were turned into the earth, as we read in verses 9 to 11. The waters above are still in place, as we see in Psalm 148. "Praise him, ye heavens of heavens, and ye waters that be above the heavens." The background radiation, first discovered by Penzias and Wilson in 1964, is almost certainly the signature of the waters above. Pierre-Marie Robitaille is a master of spectroscopy and imaging technology. His knowledge of spectra led him to revolutionary progress in nuclear magnetic resonance imaging. It led him to recognize the famous picture of a black hole to be a forgery. And it led him to conclude that the cosmic background radiation is probably due to water. The energy of the firmament is enclosed between the waters above and the waters below. The firmament of the heavens is what we normally call space. The energy which fills it is almost certainly what led scientists to the concept of ether. It's almost certainly what is now called zero-point energy. It does not fill billions of imaginary light years of a Big Bang universe stretching off to infinity, as Claudia Rham tells us. It's contained within the waters above. So at the end of the third day of creation, we have the waters below changed into the earth, pretty much as we know it, surrounded with space full of energy, and the waters above forming the boundary of the universe. And God made two great lights, the greater light to rule the day, and the lesser light to rule the night. He made the stars also. And God set them in the firmament of the heaven to give light upon the earth. So by the end of the fourth day, we have the universe, finite and bounded, with the earth at the centre, surrounded by space, populated with stars. Well, that disagrees drastically with any kind of Big Bang universe. And I can hear cosmologists and the astronomers saying, but what about all those vast billions of light years we've measured by their redshifts? Well, that's dealt with in episode 49. But in case you haven't seen it, we can look at it now. We saw last time that only a narrow beam of light will shine from a star directly onto the Earth. Most of the light from the star will be reflected from the waters above. Our experience with mirrors in everyday life may give us an idea of what to expect from reflections from the waters above. I'm sure many of us have been in a lift with mirrors on opposite sides. You see your reflection alternately back and front, disappearing into the distance. This used to be a popular theme in films. One of the most famous being Orson Welles' classic Citizen Kane. We see the right side of Mr. Kane, then the reflection of his left side in the mirror, then the reflection of his right side from the mirror behind us, and so on. The distances between the left and right side reflections indicate the difference between Mr. Kane's distance from the two mirrors. The images become smaller, less distinct and fainter as they fade away into the distance. There's always loss of energy and clarity with every reflection from any surface. The energy of light depends on the frequency or wavelength. The higher the energy, the higher the frequency, and the shorter the wavelength. At each reflection, there is a loss of energy. So the frequency is reduced, and the wavelength increases at every reflection. This is commonly known as redshift. At every reflection of starlight from the waters above, there will be a loss of energy and a corresponding increase in redshift. When William Tift discovered that the redshift measured by astronomers do not change continuously, but in distinct steps, the expanding universe idea was shown to be nonsense. The Earth would have to be surrounded by distinct shells moving at different speeds. The Big Bang should have been abandoned, but the establishment's best in the field dictum does not allow a disproved hypothesis to be rejected until another theory, acceptable to the establishment, has been approved. An even clearer indication that the whole story was untenable came when some of the measured redshifts corresponded to galaxies moving away from us faster than the speed of light. If they're moving away faster than the speed of light, how could light from them ever reach us? Well, perhaps Einstein's and Minkowski's mathematics can explain it away, but how could anyone with any sense fail to see that reality carries more weight than fairy tales? Repeated reflections from the waters above lead to quantized redshifts automatically, and there is no connection between redshift and speed. Redshift depends only on the number of reflections. Seen from the Earth in any direction, the surface of the waters above will be almost flat for a small area. there will be another almost flat area on the opposite side of the universe, so we might expect something similar to the reflections of Citizen Kane in every direction. And for small areas, one might consider almost flat sections at other angles. One bottle of scent between mirrors at 45 degrees looks like 8 bottles. But we have almost flat areas at every possible orientation. That might present us with a vast number of images. If we look at one girl and a light, with 1 or 2 mirrors at different angles, we see a lot of lights and a lot of girls. She's quite close to one mirror and much further away from the other. So her reflections are in groups of 2 with large spaces between them. About 5 or 6 lines of groups can be made out before they become too dim and small to distinguish. But with a telescope, it would be possible to make out many more disappearing into the distance. The groups tend to form lines with gaps between them, which depend on the spacing of the mirrors. Can this tell us anything about what we would expect to see as we look at the stars? It would seem fairly reasonable to expect that the stars, and possibly the first reflections of stars close to the waters above, would appear bright and clear. First reflections from the waters above on the opposite side of the universe would probably be much fainter, but probably still quite clear. Second and higher reflections would probably be progressively dimmer, more degraded, and only visible with a telescope. But with the stars, we cannot just look at the reflection of one star at a time. All of the stars are shining. The reflections may be superimposed. There may be some which have reflected many times, which appear to be right next to some which have been reflected only a few times. Would it come as any surprise to find a slice of the Sloan Digital Sky Survey looking like the image on the survey website? I don't think it would be any surprise at all. We see lines of arcs of many images separated by areas with few images. The distances between the dense arcs probably has something to do with the distance from one side of the waters above to the other. The images get dimmer with distance from the centre. No surprise there. The greater the apparent distance, the more times the light has been reflected from one side of the heavens to the other, and the more energy has been lost. I think it's obvious that the structure of the universe described in Genesis chapter 1 explains the astronomical observations very well. Both the cosmic background radiation and the apparent distribution of stars are explained far better than the Big Bang explains them. But can we expect the scientific establishment to abandon this totally discredited, tattered remnant of a failed hypothesis? I don't think so. Many eminent scientists have pointed out for many years that it can't be true. But the likes of John Maddox and Fred Hoyle have been pushed aside. Society continues to bow before the pronouncement that something is scientific. I think instead we should take note of what 1 Corinthians 1 verse 20 tells us. Hath not God made foolish the wisdom of this world? Thank you for joining me for this episode. If you enjoyed it, please like, subscribe and press the bell so that you'll be notified as I release new movies. If you'd like to support this project, you're welcome to do so through Patreon. Find a link on my channel banner and in the description below.